unmanned aerial vehicles has contributed a great deal to the advancement of geospatial technologies for fine-scale mapping, monitoring, and inspection applications. We have developed a UAV system with autonomous inspection capacity by integrating GPS, IMU, LiDAR, camera, and ultra-wideband sensors. The UAV system is named the Quality-Driven Drone or Q-Drone. For Q-Drone system, positioning of the UAV is essential. However, in GNSS-denied environment, these technologies fail to provide accurate position estimations. An emerging solution for positioning in GNSS-denied environment is Ultra-Wideband ranging technology due to its centimeter-level accuracy and robustness to multipath and non-line-of-sight effects. Long ranges can be measured up to few hundred meters with acquisition rate of up to 100 Hz, and it also has lightweight, low power consumption characteristics. The problem of UAV positioning can be formulated as estimating the location of the UWB tag relative to the anchors. To address this problem, multilateration techniques can be used. For reducing uncertainty in the estimated position, the anchors must not be coplanar or near coplanar. However, in real-world operational circumstances, this condition cannot always be satisfied. Ill-configured anchors result in an ambiguity in positioning solution known as flip ambiguity. Flip ambiguity results in two possible solutions for the tag, one below the anchor plane and another above the anchor plane, which can cause huge error if we take flip solution. There are several approaches for detecting flip ambiguity in 3D multilateration, but none proposes a method for correcting the potentially flipped solution. In this study, we present a multilateration approach which automatically resolves the flip ambiguity. The proposed multilateration approach consists of three significant steps. First, given a set of range observation and known position of anchors, the position XS1 of the UWB tag is algebraically estimated. In step 2, XS1 is corrected if it is considered flipped. This correction is made by symmetric reflection of XS1 with respect to the plane formed by the anchors, resulting in XS2. In the last step, XS2 is refined to XS3 via nonlinear optimization. The first step is algebraic solution on tag position. This solution follows the work of Norton 2012. Given a set of range observation and the known position of anchors in the anchor frame, we can estimate the approximate position of tag by solving the system equations. This system can be solved using recursive scales. Step 2 is resolving flip ambiguity. To resolve the flip ambiguity, we assume that XS1 is flipped when height of UAV is negative. By this rule, XS1 is classified into flipped or non-flipped. X flipped is corrected to new solution X corrected, while X non-flipped is moved to the next step without further corrections. The correction is performed by symmetrically reflecting X flipped with respect to the anchor plane. First, we find plane equation using current anchor positions and then calculate distance between the flip solution and the plane. By subtracting the distance twice to plane vector direction, we can achieve corrected solution. The last step is to refine the solution using nonlinear optimization. We refine XS2 to XS3 by solving the following equation. Here, XS2 is used as an initial approximation of XS3 in optimization. We use Levenberg-Marquardt algorithm for this optimization. As a result, we obtain XS3, which is final output of our multilateration approach. We use the robotic total station Leica Nova MS-60 to measure our ground truth position of the UAV. The multi-station tracked the prism attached to the UAV and provided its position at frequency of 10 Hz with millimeter level accuracy. The time of the multi-station and the UAV were synchronized by comparing height measurement from multi-station and inertial measurement unit integrated to the UAV. In this experiment, we acquired 5 data sets, manually navigating the UAV in different patterns. The specification of acquired data sets are summarized in the table. These are results of our multilateration. We use mean absolute error for evaluation. It can be concluded that our proposed approach for resolving correcting flip ambiguity could improve accuracy of UAV positioning significantly. This figure shows the error in the initial solution XS1, which was estimated using the approach of Norton 2012. To clarify the errors caused directly by flip ambiguity, we separately present the errors in X-flipped and X-non-flipped. As it can be seen, flip ambiguity caused gross positioning errors that could not be neglected. Positioning information with this level of accuracy could have severe consequences if used navigating the UAV. This figure shows the impact of proposed method for resolving and correcting flip ambiguity. The errors caused by flip ambiguity could be significantly reduced by proposed correction method. This figure shows the impact of positioning refinement by variable market nonlinear optimization. It can be noticed that nonlinear optimization slightly enhanced the accuracy of positioning. Here's the result of set 1 visualized in 3D. Blinking red dot is result of step 1, and blue dot is result of step 2, and magenta dot is result of step 3, and green dot is ground truth. Here's our conclusion. We present multilateration approach for positioning UAV in GNSS-denied environments. Compared to state-of-the-art, the proposed multilateration approach benefits from an algorithm for resolving and correcting flip ambiguities. Through the experiments in real-world environment, we demonstrate that the proposed solution could effectively resolve the positioning errors caused by flip ambiguity. In general, an improvement of 9.68 in UAV positioning accuracy was achieved by correcting the impact of flip ambiguities. Then the results were further improved by 6.02 through the nonlinear optimization. In average, our complete UWB positioning workflow resulted in an average indoor positioning error of 0.125 meter. Thank you for listening.